Hi everyone, this is day 2 of lesson 1.6, Modeling with Linear Functions. And here's our first example. The cost of parking in a parking garage in Chicago is represented by the equation y equals 15x plus 20, where y is the total cost in dollars and x is the time. So a parking garage in Chicago is represented by this equation. Second piece of information that we have is that this table down below shows the cost to park in a parking garage in Denver. So we have parking in Denver, parking in Chicago, one represented by a table, the other by an equation. We want to know which city's parking garage charges more per hour and how much more. So more per hour and how much more. And finally, we want to know if there's a point in time where the cities would cost the same. How many hours would it take for both cities to cost the same? All right, so right now we have an equation for one of our cities, Chicago, and we have a table for the other. So it's going to be very difficult for us to compare table to equation. So I would like to change the table into an equation. We learned how to do that last time using Desmos, and then it'll be easier to compare. So let's go ahead and use Desmos to take this table of data and make an equation out of it. I'm also going to note here, I'm just going to write that Chicago is this equation. That way I have it handy. And then I want to know what Denver's equation is. That's what I'm trying to find right now. Y equals what? Let's find that out. So let's run to Desmos and put in your table of data just like we practiced last time. Remember that you hit the plus key and then select table. I've already done this here, and I've used the zoom to look at all of my data at once. Now recall from last time as well that in order to get Desmos to estimate a line and in slope-intercept form, we just need to write the slope-intercept form, but in a little bit of a special way. So we're going to write y1 is approximated by mx1 plus b. And we can get our parameters that we need. Our m is equal to 8 and b is equal to 27. You could even touch the dot there and see that our intercept is at 0, 27. So we're going to use those two pieces of information and go back to our notes and create our equation. All right, so Denver was 8x plus 27. And the question is now, comparing these two graphs, which one charges more per hour? Per hour, that sounds like a slope to me. Cost per hour. So we are going to look at that cost. All right, so our cost per hour in Chicago is 15. Our cost per hour in Denver is 8. So we can clearly see that per hour, Chicago is charging more because they're charging 15 and Denver is only charging 8. So Chicago charges how much more? Well, 15 minus 8 is 7, so $7 more per hour. And that answers our first question. So Chicago charges $7 more per hour. Now we want to know how much time would have to pass for parking in both cities to be the same. So if we want both cities' parking to be the same, that means that the equations have to be equal. The y's have to be equal. So we can set those equal to each other. We can do that by hand and solve for x, or we can use the power of Desmos to do that work for us, and that's what we're going to try. So we're going to say that the cost being the same is the intersection of these two lines. It's where these two lines cross in Desmos. So we're going to jump back over to Desmos and put in both of our equations now. So let's go over there. And I have typed in the equation for Chicago. You can see that in blue. And you can see the equation for Denver in green. And we want to know the intersection. And the intersection is a 1,35. Remember, the x is hours and y is the cost. So after 1 hour, they both cost $35. Back over here then, how many hours do we have to stay in the parking before both cities are the same? Well, they're the same after 1 hour because x was equal to 1. So same after 1 hour. So what we did with this data table is that we created what's called a line of best fit. That's a vocabulary term that you're going to want to be familiar with. So a line of best fit is just a line that lies as close as possible to all the data points. And we can say that that's on a scatter plot because we created a scatter plot from that data. All right, we are done with our first example.